Firstly, we will talk about a short brief of support vector machine model and the kernel trick in SVM, and a logarithmic kernel function and experimental results. Mainly, this talk will be on a paper which is a joint work with Nurullah Çalık and Serpil Üstebay from Istanbul Medeniyet University Computer Science Department. Lastly, we will talk about the completely monotone functions and machine learning. Support vector machine, one of the most well-known methods for classification and regression is support vector machine. However, there are many alternatives to SVM, such as Bayesian networks, k-nearest neighbor classifiers, artificial neural networks, and decision trees. Each of these methods has its own advantages. Some are easier to use and faster, others may be slower or more sensitive to parameter choices. Among these methods, SVM is widely used because it has a strong mathematical foundation, works well in many cases, and can generalize effectively using different kernel functions. SVMs are applied in many different practical domains like biosequence analysis, object recognition, text classification, and speaker identification. SVM stands as a mathematically well-defined technique that holds the potential to achieve a performance level nearly equivalent to more complex approaches like neural networks in both classification and regression tasks. It is a kernel-based method denoting the utilization of a kernel to transform data into a high-dimensional feature space, facilitating the deployment of linear classifiers. Here I want to note that the difficult part of this study is to compete with the complex models like neural networks, because computer scientists call them as the state-of-the-art models, and they have good performance, but as all know, they are not robust, or they don't give stable results all the time. So mathematically founded models also need research and can be combined also with these deep learning techniques. And the principal strength of SVM resides in its flexibility, which stems from its ability to employ a custom kernel. Central to the efficiency of SVM is the selection of a suitable kernel. Now, as I said, there are the neural networks, the state-of-the-art models, and the mathematically founded models like support vector machine. Now, people generally think that data science always have very big amounts of data, but many practical applications have small data sets. And here we focus on the small data sets. So since small is a modest world, it can be seen as is it important, or does it have real applications? So here, and also, isn't it easy? Here in this slide, I wanted to answer these questions shortly. Small data sets also have some challenges, like overfitting, because you have very small data set, models may memorize patterns instead of generalizing well. Lack of diversity, the data set may not represent the true distribution of the problems. And difficulty in validation, splitting data into training and testing may leave too few samples for reliable evaluation. So these are also challenges for small data sets, and they need to be searched with importance, with care. And the second slide shows us some example applications of small data sets. And the first one is a case, medical diagnosis and rare diseases example. If you are searching a data science problem for a rare disease like ALS or certain cancers, you can't have a big data set. You have a small data set, and rare conditions mean fewer patient cases are available. So it is an application area that we have small data sets. And here also, I think it's important to note that small data sets are not as small as we think sometimes. For example, data sets less than 10,000 rows are considered as small data sets. So they are not very small always. Quality control example also, another application. In manufacturing example, you are testing medical devices. So you have very small defective samples, and it is also an example of small data set. Another application example is personalized recommendation systems. You have a recommendation system, you are recommending books or movies to the audience, but if you are not Amazon or don't you have an Amazon scale data, you don't have enough knowledge, enough information, and you have a small data. And also there are new users who have little or no knowledge at all about giving recommendation to them. And SVM has another importance, which is very important these days, because SVM can be seen as an energy-saving, sustainable ML model. We see that big data sets need more computation, and if you don't need it, why do you use so much energy? So classical machine learning models like SVM play a crucial role in energy-efficient computing, especially in environmental applications. Unlike deep learning models that require extensive computational resources and large datasets, SVMs can achieve high accuracy with fewer samples and lower energy consumption, so they contribute to sustainable AI practices this way. Now, the kernel trick in SVM. Research on different kernel functions is still an active area, not only for SVM, but here we will focus generally on SVM kernels. Some of the first kernels used were linear and polynomial kernels. Also, this sigmoid kernel appears, and it is not a positive definite kernel or a Mercer kernel, and it works. But we see that if we don't have a mathematically stable kernel like sigmoid kernel, it can work well for some data sets, but also in many data sets, it has convergence problems, ill-conditioned matrices, and so computation problems. The radial basis function is the most commonly used SVM classification kernel. Researchers continue to explore the best kernels for different types of data, such as sound signals, genome analysis, and intrusion detection. So we can say that every dataset has an optimal kernel that fits its characteristics. Now, these are the conventional kernels. Firstly, the RBF or Gaussian kernel, in other words, sigmoid kernel or tan hyperbolic kernel, in other words, polynomial kernel, and linear kernel. And also, there are some recent kernels which are the results of new research on new kernels. Here in this study, we tried all of them, and since we found out that UKF, Lorentzian function kernel, competes with our kernel, the logarithmic kernel function, very well, we generally used it for comparison. The primary objective of SVM algorithm revolves around the identification of the hyperplane that yields the maximal margin within the data space. Suppose a training data has an input vectors and associated labels +1 or -1. For example, in a data set, scoliosis data set, we will talk about it. There are images which are normal or scoliosis, and we label scoliosis with -1 and the normal image with +1, for example. So here, SVM tries to establish a decision boundary, this one. And we want that there are equal distances from this decision boundary to the support vectors. What are support vectors? Support vectors are mainly or basically can be understood as the nearest vectors to the other class from the +1 class. And also the red one can be considered as the nearest element, which is nearest to this class. And we want this margin to be as big as possible, as wide as possible, to have a robust, to have a stable classification. But also we will say that in real world, this is not possible. There will be crossing nodes. So we will talk about it later. SVM aims to find the optimal separation hyperplane that separates the data with maximum margin. The equation of the separation hyperplane H is W transpose X plus B equals 0. Here W is the vector of weights that determines H plane, and B stands for the bias. The objective of the SVM algorithm is to find the optimal solution for the following problem. In equation 1, here, the maximum margin is given by gamma, 1 over norm omega. So we are trying to minimize the norm of weight vectors. And so we will do the margin as big as possible. However, real-world data is often complex and not always perfectly separable. To handle this, slack variables are introduced. These variables allow some data points to cross the margin, making the model more flexible. We can think it as we allow some points to go to the other sides, from minus to plus or plus to minus side. As a result, the original optimization problem is modified like this. Furthermore, the introduction of a penalty parameter C allows the control of these slack variables here. And in this stage, we focus on a nonlinear data set because many real-world problems are not linearly separable. They are nonlinear. And this nonlinear data set that proves unsuitable for linear separation is handled. To address that challenge, a transformation of the data into a high-dimensional feature space is employed. And we will look for a linear discriminant analysis, a linear classification in this new feature space. The nonlinear transformation can be represented as phi x is going from the RD to R capital D space. The optimization problem so changed to that for formula. Here we replace the xe with phi xe, the mapping of these features. So we are now working on the in the feature space, a high dimensional space generally. Herein, the capital D can be infinite dimension also when using proper kernels like RBF also, or like the logarithmic kernel function we use here. In SVM implementation, the Lagrangian optimization problem leads to a dual form of the original SVM problem. This change is driven by the computational efficiency of calculating Lagrange multipliers. So we can use dot product for computations like in 6. Here Q is a matrix, and n by n positive semi-definite matrix. It is established by the help of K function. Alpha I are Lagrange multipliers, and non-zero alpha I correspond to support vectors. Here K stands for the kernel function. The kernel function facilitates the transformation of data into a higher dimensional space. But now we don't need to compute K. Phi itself, we only need to compute K, because if we can compute K without computing phi, it will be computation saving. So the last form of the classifier function is classically used like formula 7. This is the sine function, and it gives plus 1 or minus 1. And we say that this belongs to this class or this class. But also, this is not the only classifier function. There can be used some Bayesian functions which give a probability of being belonged to a class also, or other classified functions. Distinct kernel functions arise from various mappings. As the computation phi is unnecessary, a more beneficial approach is to concentrate on the kernel function and their properties briefly. And this approach enables the application of various potential kernel functions using the same methodology. But this new section is logarithmic kernel function, LKF and experimental results. Here, I want to note that it seems very simple. If we use any positive definite function, then it will work, we hope. But as a person who tried one more than a couple of hundreds functions on different data sets myself, theoretical results they don't guarantee the application of these kernels in real world data sets. So it is not so common. It is very rare that you can get a function which also satisfies the theoretical results and also works well with the data sets, real data sets. And now we'll start about the establishment of logarithmic kernel function and its theoretical parts. The existence of a function that embeds the original space into the augmented feature space is assured by Mercer's theorem for a non-negative kernel function K. Mercer's theorem implies that kernels should be symmetric, continuous, and positive semi-definite. Then their kernel matrices have all non-negative eigenvalues. The use of such a kernel ensures that the optimization problem is convex and uniquely solvable. The following theorem gives a way of identifying positive definite functions. This is the main part of our paper. As far as I read before, I didn't see any kernel function which is established from such type of mathematical view to use in machine learning or any other application area. So here, this is a classical theorem on completely monotone functions. It says, if GT is a non-constant function, continuous and completely monotone, then you can put R square instead of R, and you can establish phi R, which is a positive definite function in any d-dimensional space. As a consequence of theorem 2, there occurs a way of defining new Mercer kernels by assigning R equal to norm of xi minus xj. This is a Gaussian-like kernel saw. And firstly, I thought that it would work similar to Gauss function, but we will see together that the experimental results showed that this is better. This type of GR square functions satisfy all properties of theorem 1, and this is the origin of the idea behind design of LKF. And this is the paper I'm talking about, and this is my student's master thesis. And first, we mentioned about this type of kernel instruction in this thesis. Along with the Mercer condition, there is an additional requirement called the soft condition for a function to be considered a Mercer kernel. This condition states that the kernel function should have two key properties. It should decrease quickly near zero and slowly as values move towards infinity. The slow decrease at infinity helps maintain the closeness of information as values decrease. This is important. Why? Because we here use K as the similarity measure, some type of. So if you have a small data set, and then we want to use all points, every point. So if they are very close to each other and the kernel function goes to zero very rapidly in the infinity, we cannot use that. And instead of a positive number, we get a zero and sparse matrices and the problems. Another thing I didn't note here is the scaling problem. There are many completely monotone functions, but they have some of them can be very big, and they need some scaling after the process and after the mapping process. And also this needs some more computation load. And also some of the kernels have more than one parameters. If you have more parameters, possibly the kernel will work better, but it will have more time to compute these kernels in optimization procedure. So having less parameters is good, and starting with one and going to zero is also another good property of the function we established. This study suggests that completely monotone functions could be useful as Mercer kernels. However, tests during the research showed that many of the kernel candidates created using these functions did not perform well in classification and regression tasks. Many of these functions struggled to meet the necessary conditions also to be considered Mercer kernels. Among all the tested functions, LKF was the most suitable, meeting both the theoretical and practical conditions to qualify as a Mercer kernel. Additionally, LKF showed a regularizing effect by assigning strictly positive values to distant points in the kernel matrix, and it results in a non-sparse matrix, and it works well for these tasks. And we will come to the LKF. This is the logarithmic kernel function. Here E is the Euler constant. We have only one parameter alpha positive, and this is the natural logarithmic function. This is easy to implement in Python or also MATLAB since it doesn't have any special function in definition or any other thing. It was easy to implement also. This is another advantage. Corollary that alpha positive LKF defined on a compact domain X is a Mercer kernel. Here a single variable logarithmic function is considered fr, and then we put r square instead of r, and we get phi r. And function 11 is obviously continuous and infinitely differentiable. Computing the derivatives of 9 to a finite order k gives that this function is a completely monotone function. The application of theorem 2 says that phi r exhibits positive definiteness. Evidently, LKF is symmetric since it is a radial basis function. The completion of the Prof follows from theorem 1. Here are the graphs of LKF and RBF for the part near 0 and near infinity. We want the kernel to decrease very quickly near 0. And we see that LKF can compete with RBF. Of course, this graph does not show that it is always faster than RBF because it changes according to the parameters here. But we see that it works well. And in infinity, we can say that RBF becomes 0 very early, but LKF stands for a while. And this means that I will not have zeros for this part for LKF. But RBF, they will be 0, and the similarity is preserved here for the points which are close to each other. Herein, figures are created by MATLAB to show the soft conditions for LKF. And these are my also comments before. Kernel functions are generally divided into two main types: dot product kernels like linear polynomial kernels, or distance-based kernels like RBF. The term RBF here, differently from mathematical side, pertains to real-valued functions that are exclusively dependent on the distance between the input and a predetermined point. And now we are coming to the experimental results. Here is the illustration of the optimization procedure. Here I want to thank to my colleagues Nurullah Çalık and Serpil Üstebay because they brought the paper into a more advanced level with their implementations and optimization procedures. So this part appeals to computer scientists more. And here are the description of the classification datasets, regression datasets. These are classical datasets that are used for newly established models and kernels, etc. Now let us see table 3 together. These are the classification results over first 3 datasets. And here we see accuracy, FCM, FSM values. Since we can comment on them like that. If they are near to 100, they work good, they work well. And for the first data set, for the first random test part, we see that LKF is better generally. For example, here RBF passes LKF, and also this. the 70% ratio, RBF passes. But here, LKF is better. Here, LKF is better for all of them. Here, LKF is better for all of them. And overall, LKF shows a good performance also compared with the UKF, which is a good working new kernel in the literature, new literature. Table 4 shows the other classification data sets also. Here we see also here LKF is better. Here again in 70% ratio, RBF passes this. And here also RBF is slightly better. No, not RBF, UKF is better. And here LKF is best. And here LKF is competing with competing with UKF. And here also LKF is better. Again, here we have the regression performances of kernels. There are regression tasks, and here TP optimization is implemented, and they repeated this for 10 times to get a mean value and the standard deviations here. Here, mean absolute error and root mean square error are presented, and we expect these errors to be small to be a good kernel. So here LKF is best, and here LKF is competing with tan hyperbole kernel, but here it is best, and here it is far away best, here also, and here and here. For this data set, it worked very well. And at other regression tasks, here it is very good for this data set. It is better than for this data set than the other kernels, and it is the also best one. Not best, maybe here there is a passing. Yes, but for these values, LKF performs better. As we said, the best kernel changes to the type of the data set, of course, so these are possible. The other important table is about the training time, because we said this is an energy saving process, and maybe changing the kernel can also help with the energy saving. And to do this, it should take less time to do these computations. So we will see about the time which passed during these data sets tasks. And we see that LKF is the best for all of them. It has the shortest time. And when we compare with tan hyperbole, which is a sigmoid kernel, which is not positive semi-definite, we see that it is very, very easy to compute. And also support vector numbers are presented here, which means that if you have a less support vector number, this means your model is not very likely to overfit, because you have a small amount of points that your model is established on, constructed on, so it is more robust or more stable. So we see that support vector number is also the best for the LKF kernel. Now, the section is completely monotone functions and ML. A positive function defined on zero infinity of the class C infinity, such that the sequence of its derivatives alternates signs at every point, is called completely monotone. This topic was developed in 1920s, 30s by Bernstein, Hausdorff, and Widder. And there are more properties of completely monotone functions in these books and papers. Definition of a completely monotone function: if the f defined on zero infinity is completely monotone, it has derivatives of all orders which satisfy this inequality. And these are some limit properties which help also the completely monotone functions to be appropriate kernel functions. By definition of SCM, completely monotone function, there exist limits of fkx as x goes to 0. If those limits are finite, then f can be extended to 0 to infinity. Limits at 0 need not be finite, as in 1 over x, for example. Clearly, And so this means that not all functions can be appropriate for such kernels. And the limit of f at infinity must be finite. And if it is non-zero, then it has to be positive. For example, like this, in this function example. Now for other research topics that are related with completely monotone functions and machine learning, there are a long list of models, of course. But here, I brought here the most interesting topics for me as a mathematician: support vector machines, kernel-rich regression, kernel PCA, and kernel k-means algorithms. They use kernels. And for as mathematical sides, this type of functions also have some other interesting properties, because Mercer's theorem can also again used for different types of positive definite kernels in Hilbert spaces. And also these kernel spaces are called by reproducing kernel Hilbert spaces. And here foundations of functional spaces where function evaluations are inner products with kernels. There are many papers on functional analysis part of these kernel functions also. And mesh-free methods for PDEs using kernel-based interpolation to solve PDEs. Since I am working also on fractional differential equations, there are works to do about such type of mesh-free methods on fractional PDEs. And also I want to note an ongoing research, ensemble methods about the SVM and the deep learning together. Because since we have such type of deep learning and transfer learning techniques that are very useful, especially for image recognition, we want to use it, but we want to use also SVM and its kernel as a classifier here to make the process more accurate. And we are trying this on a scoliosis dataset with my master student, and this is her master thesis. And she is about to defend it in a few months. Here we have a dataset which consists of normal or scoliosis X-ray images. And we are trying to classify the images into that with firstly using deep learning and transfer learning and getting the feature vectors and getting these feature vectors as a matrix, giving these feature vectors as a matrix to the SVM for classification, like a small data sets, which consist of only numbers, not images anymore. So I'm looking forward for the results of this research also. And there is the funding research part. Application of such type of kernel functions on real data sets was an interesting topic. And here, Yasin Bulut and Mehmet Taşgetiren are the managers of this TÜBİTAK project. And I am the supervisor about the mathematical part of this decision support system. And this is my student, undergraduate student, and her project, again, using singular value decomposition on sea surface temperature estimation, but here we use the regularization, the P regularization, but we then saw that the kernel functions can also be helpful for kernel ridge regression of this dataset. So we will use also kernel functions in this project. Thanks for your attention. These are my emails. I would be more than happy if anyone interested can reach out to me, or want this presentation or my paper, I will send as soon as possible. Thanks.